now for something completely different, as I said. I'm going to talk about tall building weights in a real urban area, and the real urban area being London. I'd like to acknowledge my co-authors, especially Janet Barlow, who unfortunately couldn't be here this week, but she was very, very involved in a lot of the work. Why study tall buildings? So this is just a figure of the amount of tall buildings above 200 meters being built in the last, since the 1980s. So each year, what's being built. So, I mean, we see that we have an increasing number of very tall buildings being built in the most recent years, since the 80s. So we want to know what their influence is on the atmosphere. Now we know this classical picture from, as Mona said, our Bible. So we know that, this is just a cube, an isolated cube, and what its influence is on the flow. So we know the oncoming flow, we know it's being displaced, you have a displacement zone B due to the pressure deficit. Then you have a cavity close to the building, or cube, or whatever. And then you have a wake behind. So, but what actually happens when we put this cube into a real urban area? So there have been some studies that looked at this, especially in the wind tunnel. So these are some examples of tall buildings in an urban setting. This is London, the area we looked at, but also some other studies looking at tall buildings. And the second method that people tend to use is LES or RAND experiments, CFD experiments. And the nice thing about LES is that you can also look at stability, which is a bit more tricky to do in the wind tunnel, as Mark can tell you. But what actually happens in real life? Can we actually observe these wakes in a real urban area? So for that, we moved to London, and especially the south of the river, where there are a lot of tall buildings popping up in most recent years. So this is the study area here, south of the River Thames, and we put a Doppler wind lidar, which I don't have to introduce anymore, on top of a roof here at the university. To measure these weights. And for stability, so looking at stability a bit later during the talk, we also use measurement sites of BT Tower, which is a very tall tower, weather eddy covariance measurements. So just a bit more impression of the measurement site itself. So over here, just move here. So here's the Doppler lidar. And this is just a view from the roof. And over here we have an eddy covariance measurement station, which we also use for stability analysis. There are a few tall buildings you can see here. You can see some very far away, and you can see some close by, and these ones. And I'm just going to focus on these ones during the talk, because unfortunately we couldn't see this building because of all the stuff that's on the roof here. So that's a tip for placement. I mean, look at what your lidar can see before placing it. But we can see these buildings. So just another view of the sites just from above. So here is the lidar place at about 33 meters, and these are the buildings that you can see here. And what we do is with LiDAR, we do 3 different scans for a year with a resolution of 18 meters. So we start with the simple stare. So basically the laser is pointing upwards, and because you're pointing upwards, the Doppler LiDAR can see you can derive the vertical velocity at quite a high frequency. So this is 1 second, 1 hertz. But we also do fat 75-degree scans, which is just a cone for which you can derive the wind speed and wind direction and the UV components of the wind. And you can get something like this. So this is the wind speed and this is the wind direction for a particular day. But then, more importantly, we do 0 degrees flat scans, which basically means we're scanning flat, over the city basically, and we do this once every 12 minutes. So we have, for a year of data, we've quite a lot of scans. So can we actually see anything with the slider when doing these scans? So here I put these are the building heights basically, and the big red circle is where the LiDAR is, and all the blue areas are above 33.5 meters. So this is something that potentially the LiDAR could see. So if we look at the LiDAR data, so this is the backscatter from the LiDAR, with again these 100-meter radiuses, just to see. And what you can see is that these building A and building B, you can see quite clearly in the backscatter. And you can also see these buildings over here. I don't know if you can see the pointer really well. You can see them in the backscatter. So we can see buildings. So that's something. So can we actually see wakes? So this is just one of the instantaneous scans. So this is one of these scans that we do once every 12 minutes. So looking at this initially, we thought, oh, okay, it's a bit disappointing. Blue is negative radial velocities, which is towards the LiDAR, and the positive red colors are away from the LiDAR, so the wind is coming from northeast. So to get something out of these images, we try and calculate a radial velocity average, and we do this by fitting a sine curve through each of these arranged gates. So every distance from the LiDAR. So we fit a sine curve, and from that we can get the wind speed and direction for each distance from LiDAR, and from that we average this in a radius of 700 meters. So then we get this averaged radial velocity here, and we subtract that from this instantaneous field, and then we get a difference. I think I have my time's up left, right?
You have time.
And you see some deviations from the average wind speed. So you see some speeding up of the wind, and you see some slowing down, but you don't really see any wakes yet. So, but we have a lot of data. So we have a year of data. So what I did is I average everything for the predominant wind direction to start with, because that's when we have the most data. So on the left here, you see the radial velocity that you get from that, and then you do start to see some differences. So, and this is the velocity deficit that you get from there, and then we see wakes. So yeah, so we are quite happy with that. And you see wakes from each of these high regions of backscatter. So even from the bit of the small, these are tops of buildings and some trees. But from building A and building B, you do get wakes, which is quite nice. So we were very happy with that. But yeah, so what you can also do is just draw a cross section through this wake. So this is a cross section through the wake, and because we have a lot of data, we could also differentiate between different stabilities. And the stabilities we calculated were based on the Bukov length at the BT tower site, so this big tall tower, but also from the eddy covariance measurements on the rooftop height. But also because we did these stairs with the vertical velocity, we can get the boundary layer height, and that we also used as a stability. So the stable conditions are very shallow boundary layers with high Bukov length, and the unstable cases are deep boundary layers with large negative. We don't see much difference in stability, for the cross-section wake. But if you look at the wake parallel, also at the cross-section parallel to the wind direction, you do see something. So for these very unstable cases, you do see that the wake doesn't last as long, so it doesn't go as far. So it only goes to 100 meters, while the other wakes they continue. So you can also do this for different wind directions. So this is the wind coming from the northwest, sorry, which we have a bit less data for, and especially in an urban area, we don't have much stable cases, so the stable ones are the first to go, basically. But you do see see wakes that go up until 200 meters, and you do see some influence of the during unstable conditions that the wakes tend to die out a little bit more, and they're a bit weaker. But so just to summarize. So we can measure wakes, building wakes, with the Doppler lidar, which we were very happy about. So because of the turbulence, I mean, you need to do some averaging to get them out. So we recommend measuring over longer periods. But what I didn't show is, so there's some influence of stability, but what I didn't show is if the building wakes are influenced by other building wakes. So there are multiple building wakes downstream. The building wakes downstream tend to not have this effect of stability in them. So the effect of stability seems to die out. I mean, we should do more analysis on this, but but this is what we found in our setup. So these are just 5-degree scans. What we could do is more dedicated scans with smaller degrees, basically smaller ranges. Also interesting would be to look at isolated buildings and building clusters. And because, these instantaneous scans are quite interesting, I think. Can we get some actually turbulence statistics from that? And I think that would be really interesting to investigate. So that's it from me. Thanks so much.
Questions?
Yeah, actually I was performing a LiDAR measurement also in Shenzhen, in China. And actually I was wondering, the LiDAR measurement will use full laser, which means the frequency of the measurement will depend on the frequency. So how do you, which means when we calculate velocity, it means the first laser go out and come back, go out, come back with full direction. So which means the velocity actually has a time delay. So how can you get the velocity you get, the final velocity is the true velocity, not depends on the other factors. And what's the frequency of LiDAR you use in your campaign? Thanks.
Yeah, that's a really good point. I mean, so these flat scans, they take about 1.5 minutes. So that's the variation that you get. This is something that should be tested, of course. At this moment, we don't take this into account, and also because we do a lot of averaging, then that goes out. I think once you start looking at turbulence, this is more of an issue, maybe. Mm-hmm. But at the moment we don't.
Any more questions? Yes.
I maybe a little bit of a silly simple question, but if we wanted to do a similar approach, then how long do you recommend to do a long enough period of observation to average correctly? Like if we did 1 month, would the averaging be any good?
It depends. I mean, I think if you focus on particular buildings, you could get away with shorter periods, of course. This is the thing, right? I mean, it depends how small, how detailed you want to look at. I mean, if you want to do several statistics classes or something like that. I mean, we had to throw away a lot of data because we didn't have the right stability class. So I think a year for us was good, but yeah, I mean it depends if you. Yeah, we can talk about it.
Yeah, sorry. Thank you.
Thank you.